Okay, we are back with Unix, and we were talking about signals, and let us continue talking about signals. So signals is when either the user or the hardware or another software sends a interrupt to a process that's running. And we have this example of a trapping function. We talked about this last time, where you divide by 0. Okay, we did that one. We also did, where is my, Sig user, alarm. We talked about this alarm, and here my trapping function does nothing, just return. So what happens here is if sig, wait, when does my sleep get run? Here we go. Here, I do my sleep. This function is run. Notice there's no signal handling in this program. Here, my sleep is run, and my sleep does the signal handling. And I basically handle it, right, which means I say, when sig alarm happens, run this function that does nothing. And return the number of seconds left in the sleep. We talked about this last time. I run, I do 2 seconds. So I set the alarm and I pause and I set the alarm here and I pause, which means I do nothing and I wait. Now, if somebody sends a control C, for example, well, then the whole program will end. But if somebody sends an alarm, then he will do nothing, but he'll stop the pause. In other words, if I send some signal, it doesn't kill the program. Or I send an alarm, which will do nothing. Either way, this pause will end. And as I wouldn't have this pause here, it'll also end. I mean, it won't be there. If I wouldn't have this pause here, I'll immediately do return alarm, and I will get this return alarm of 0 will tell me how many seconds I stopped early. Or how many seconds are left on the clock. So in this way, I can find out if I stopped sleeping, if my alarm went off early, essentially. Okay. Here, another example demonstrating the sending of a signal to a child process. So let's, you have a question, Jonathan? Or you did before? Okay. So where do we start to look at this program? Here at main. And it says, first I create a bunch of integers and I say, trap the signal sig user. And run the program sig user in small letters. And that's this program. Child receives sig user 1 by get PID, by whoever, whoever I am. Fine. And I check for an error. I do p error that prints an error message. And then I do a fork. I make a child. And then I say, if 0 equals child 1, that means I'm the child process. Then I do child is running, and I wait for a signal. Parent process waits 4 seconds, which is a terrible way of programming. It creates a race condition because presumably after 4 seconds, the child has finished running. But theoretically, it's a bad way to solve a race condition. Now I send to child 1 sig user 1, And then I said to the child one sig kill, which is sig kill just kills him. So first I send sig user 1, and he'll print child receives sig user 1 by, now I don't know why by, but get PID is going to be his own PID. It shouldn't really be by. It should be I am, and then my ID is, and then it should print decimal, whatever get PID returns, which is the ID of the child. Now the father kills the child, but the child will still be a zombie. He won't actually have died until I harvest the zombie with my weight. Then if I do kill child 1 with 0, remember what 0 does. 0 is no signal called 0, but 0 returns a number. It returns an error number if the child is not existent. So I print that number. This is a way of checking if the child really is not existent. Okay. Now we talked about this a little bit before. What should the operating system do if a process receives interrupt X? Well, it is in the middle of handling interrupt X. We talked about this a lot last time. On some operating systems, it ignores or blocks the interrupt until it has finished the first interrupt. Some versions of Linux do not do this. Instead, they immediately handle the second interrupt. But instead of doing the interrupt, we talked about this, no? I definitely remember. No?
Yeah, we talked about it. If it's either a FIFO or a stack, and either
Yeah.
I'll finish it or do it.
So here's the traditional behavior. We talked about that. And then we talked about sig proc max. So, and we said that with sig proc max, I can say block a signal or unblock a signal or set a mask for the signal. So let's see what Sig Action does. Example using Sig Action. So here, let's look at this. I'll put in bold, Sig Action. So here we're doing the same thing that Sig was doing before, that Signal was doing before. We're saying if I get Sig int, then do all the things that are defined in SA. And SA is going to have many, many things in it. Notice it's a pointer to a SA. What is SA? SA is a struct called Sig Action. It's like a special struct that exists. I didn't create it. Struct, notice you have to write, in Unix, you just write, in C++, you wouldn't have to write class in front of it, but here you do have to write struct. So struct Sig Action SA. And then what I do here is I say mem set. Now mem set puts a value, whatever I want. We can into this. In other words, I'm going to say put the value 0 into the structure SA in the size of SA. So size of SA, in other words, is some struct. Maybe it's got 100 bytes in it. And this is a pointer to the beginning of that struct. So this says if this says put 100 zeros starting at SA. So it'll put in every byte a 0. So I'm sort of blanking it out, making sure there's no garbage there. Because I'm going to only overwrite, I'm not going to define all the parts of it. I'm only going to define the parts of it that interest me. So I want to make sure all the other parts are defined as 0. So here I say the SA has something in it called an SA handler. And there I'm going to define what handler I want to use. So I give it the address of the handler, and that's my handler up here. That's the function that I want it to run. So when SIGINT occurs, it's going to go to whatever SA handler is, which in this case is my program above. So that's it. I just set the handler to handle SIGINT for SIGINT. What is the null? The null means the function returns 0 instead of the previous action for the signal. In other words, I could actually get a pointer here to whatever the previous behavior of the previous function that the function that Sig Action, that Sig Int would run. But instead of getting the previous function, I can just give it null, and I don't care what the previous one is. I'm defining it to do my handler. And now I do a loop only 2 times, and I sleep, and I say Sig Int was raised. Well, Sig count. Look at Sig count. Sig count is this integer here, which I made Sig atomic T Sig count 0. I made it global, and I set it to 0. So presumably every time I call this handler, Sig count will go up by 1. Because global, even if this function didn't define it. So I call this function many times, and my count goes up. So every time I press Sig Int, this Sig count will go up by 1. And then after 5 seconds, I will come here and print how big it is. Then I'll do it again. So this is just the most basic way of showing you how you can use Sig Action in the same way that you use signal. That I define the Sig handler inside of the SA to be whatever I want it to be whatever function I want it to be. But in this example, we will show how we can capture the old handler definition and set the handle back to what it was before. So here I again have my count. I again have my Sig count going up. But I have another global variable called old action. It's also of type struct Sig Action. Old action, whatever the previous action was. So I say I'm in the handle, I do sleep. And in here, now how did I get to this handler? Obviously because Sig Int came. So what do I do inside? Inside, I say Sig Int should be whatever the old action was. Now, where did I get the old action? Where did it get defined? It got defined when I did the first time Sig Action over here. Notice I wrote old action over here instead of null. Before I wrote null because I didn't care what the old previous behavior was. Now I capture the previous behavior in my global. And I give it SA again. And I do the same thing, mem set, handler. So now if I do 2 times, this only work once now. In other words, the normal default behavior of Sig Action is that every time I type Sig Int, or every time I type whatever signal I handled, it'll do my function. But what if I want to go back and make it only do it 1 time? So then I capture the old action like this, and then inside the handler, I put it back to the old action. Of course, if another Sig Int occurs during this sleep 3, then it'll still do the old behavior. Okay. Now, what about, we promised that we could mask other signals while handling a given signal. We promised that. And the way we do it is with this function called sig add set. Sig add set. As we said, by running Sig Action instead of signal, we will block further occurrences of the same signal during the handle process. Right. In other words, by default, if the same signal occurs, in other words, what I said to you before, what if during this, before I did the Sig Action, maybe another Sig Int will happen? Ah, it can't. Even if another Sig Int happens, I will ignore it. So therefore, I will definitely redefine the Sig Int to be the old action before another Sig Int is handled. So this will definitely work to only work once. But what if I want to ignore more signals than just Sig Int? So by default, it only does the one that I handled. How do I add more? So we use this sig add set. And what we say is, take that same SA that I created before, but in addition to having an SA handler, it has an SA mask. Remember before I used an SA handler. Now we're using an SA mask. It has built into it, into that struct, a mask. And I'm adding to the mask signal. So now the mask would be signal plus whatever signal I overrid, which was SIGINT. Well, whatever signal is a generic term. I didn't give this is not an example, this is like a paradigm. So we can also use sig empty set to remove all signals except the signal being handled. You cannot remove the signal being handled, but you can remove everything else by writing sig empty set. After the structure is defined to our liking, we put all the signals that we wanted to into the SA mask. We then run sig action, and then the function, in other words, I've defined that not only when a SIGINT comes should you run this handler, but also you should ignore all the signals that have been listed in my mask. By putting all these parameters in one system call, the operating system can perform it atomically. In other words, without allowing an interrupt in the middle, without context switch. Okay, in this example, we show how to mask out the additional signal sig user during the handle of SIGINT. So here we're going to do it. We make old action global so that it will be in the scope of both the main and the function handler. So here, you see, I need old action to be in the scope of the main because I'm going to define it over here, and I'm going to use it in this function. So it needs to be global. So again, I blank it out with the zeros. That's the mem set. I define the handler to be my handler. That's the SA handler inside the SA. You know, SIG, I could have called this something other than SA. And then I say, add to the set in this mask, add to it sig user 1. Then take the regular SIGINT and give it and handle its SIGINT occurrence. If a SIGINT occurs, I'm going to handle it the following way by using this SA that I just created, which is going to mean ignoring SIGINT and ignoring sig user 1. That's what SA is going to mean. And otherwise, you know, to handle it. And capture the old handle in this old action variable. And when I go up here, I am going to up the counter and I'm going to sleep. And then I'm going to allow, while I'm sleeping, a person can type control I, control I, control I. And that's going to call this function many times. Sig count will go up. And meanwhile, after when I wake up from that sleep, I'm going to put sig action back to the old action. So that again will only work once. In other words, one time it'll run the function, not many times. Oh, that's it. That's it for signals. Do people have comments or things that need to be clarified?
I just got here. I got the wrong link, so I don't really.
Well, you can watch the video.
Okay.
Well, that's a pity. We have the same link every time, no?
Yeah, I clicked the one on Moodle.
This is not the one on Moodle?
I don't know, because I got a link from someone else just now. I don't know if it's the same link.
Oh, okay. Well,
And
this
this
is
the software engineering link.
yeah, we're
One
using the software
on-
engineering link.
You should
Oh.
you should really write that on the Unix link that it's no longer.
Yeah, people figure it out.
Because I'm not in software engineering, so I don't even have access to that. Like,
Oh,
We pinned it to the Discord channel.
what?
We pinned this link that we're using now to the Discord channel for this group.
Okay, so we're gonna do some examples here, and let's do. Okay, cat signal 1 and this was the divide by 0, 1. I want to do a different one.
Is this what was the one with the divide by zero when we block the signal for the error, or
Kind of.
what's
Here, I'll
the
show you.
what's
I'll
the
show you.
how do you get the list of all the signals? It's just man signal.
Man 7 signal.
Why 7?
7 is like extra additional information or something.
All right.
There's different, the numbers are like chapters in this imaginary book called the manual.
Man.
Manual. No, if you do man, so you see about manual. It may also tell you, no, what do we do? Man 7 man. Whatever. Okay. GCC signal 1 sig now 1.c. Ooh, that's a lot of p error. It doesn't like p error. Printf. I'm missing something. Man printf. Oh. Man 2 man 3. stdio. I don't have stdio. No, I don't. Okay. You divided by 0, didn't you? Again, cat signal 1. My main here. My main does, it never printed hello because I divided by 0. Why did it go so many times? Well, that's a weird thing. It goes many times because it set an error message as being divided by 0. So that's a particularly bad error. And once I did that, it keeps sending that signal. Here, if I want to end it, I can go over here and do raise sig alarm. So if I send myself sig alarm, you divided by 0, didn't you? Alarm clock. That's the error message.
What are we trying to do?
Just demonstrating these programs.
Well, no, I understand that. What specifically right now?
I was just showing you how if I sent the alarm command, then it will kill my program.
Oh, because you set the signal for kill.
I did raise.
Oh.
Raise sends the signal to myself. And since the behavior of sig alarm is to kill, I sent to myself the kill alarm, the kill message. I died. I did it inside the handle of the divide by 0. That's what ended my program without even printing hello. Because the minute I divided by 0, it ran to over here, printed you divided by 0, and sig alarm. You see, now let's see what happens if I don't handle the signal. Just get rid of this. You see, now it's just going to divide by 0. Will it print hello this time? Floating point exception. See, it doesn't, it just tells me there was a FPE signal. That's the signal that gets set when you do divide by 0. It didn't print you divided by 0. It also didn't print hello. The minute I divided by 0, it gave me an exception. That was the normal behavior. I changed it and I made it you divided by 0. Now, let's see what signal Q is. Cat signal underscore Q. Well, well, that's not a very interesting one. That just sends a signal to myself and kills myself. This one's rather long. Let's see what I do here. Well, this is all commented. I can uncomment it. Wait a second. Hold on a second.
What are you trying to do?
Now I just wanted to make my Emacs not have its colors because I can't see it. And now I just go, wait. back where I was. Emacs signal 3. All right, so let's look at this program now. Now that I don't have colors anymore. I notice I define up here a Sig user function, and I print hello, fine. And let's get rid of this comment here. This I don't want to demonstrate right now. That would send a error. That would send a signal to this process, which probably doesn't exist. And then I could, well, we can try it actually. Let's see. And now, where does this program end? Here. Okay, so if I start the comment here, so basically the program is just going to do this line. It's going to send a signal to 999 and then print an error message. Let's see what it prints. GCC signal 3.c. So looks like I didn't declare error. But I did. Oh, this is not good. Looks better now. Except that I should have a return value. Compiles. Right? Compiles now. Hello, killing non-existent process error -1. So let's look at that again. Now that we see what it does. Here I demonstrated that by sending a kill to a process number that probably doesn't exist, error became the value -1, and I printed it over here. I can't kill a process that doesn't exist. Let's change this. Here, let's change this. Let's change it to, oh wait, let's comment. I want to comment this one out. And I want to change it to a process that does exist, like myself. So I'll do get PID. That's me. That's getting my PID. Send me the signal 0. Now it isn't a non-existent process, but now it writes 0, didn't write -1 because it does exist. It didn't kill the process because here, let's prove it didn't kill the process. How can we prove it doesn't kill the process? By running something after it. So for example, let's print that hello after it. Killing non-existent process, well, it's really myself, 0, and then hello. So you see that the kill message did not kill the process because I sent it error, I sent it error, I sent it signal 0. Signal 0 doesn't kill. It just checks whether the process is alive or not. If the process is alive, it gives me 0. If the process is dead, it gives me -1. Okay, that's the first part. Now, what else can we show you? I can show you that I can catch. Well, let me do something first. I want to do something that I didn't do. Here, let's do a I don't know if I demonstrated this before, but I want to demonstrate a different thing here. I want to demonstrate signal. I want to catch sig instead of sig user, sigint. And what function do I want to do? Could I do sig user? Yeah, I can do sig user. Doesn't do anything. Just print something. So I'm going to here. I caught sig int, and I'm telling it do the function sig user if you get it. Okay, and now I have to go to a loop that sort of waits for signals to come. So I'll do like this. For and there's my infinite loop. And in my infinite loop, I want to do pause, which means wait for a signal, but pause I think takes. Anyone remember what pause takes? I think it takes an address of an integer. I can use error again since it's available. Let's check if that's right. I'm just guessing that that's what pause takes. Man, pause. It says it takes void. So that's so fine. So I was wrong. Let's put that back. Whenever it says it takes void, you can either write the word void, or you can more simply just write nothing. So now if we run this, first I compile it. And now it's in that pause there. At first it printed that killing non-existent process that was left over from what we did before. Now it's waiting for nothing, for a signal to come. It's waiting forever for a signal to come. So if I do Control C, it says, hello, child received signal 1. And sig user 1, every time I press Control C, here I stop pressing it, and I press it again. Normally Control C kills the program. But here I'm pressing Control C, it's not killing the program. It's just receiving the signal and doing this other behavior. How am I going to kill it? I can't kill it with Control C. How can I kill it? Anybody have an idea?
Press X.
X? That doesn't help. Q
No,
doesn't.
upright. Press exit.
You try to
Oh,
bring it off and back on again.
yeah, that's pretty much the main way. Well, no, I can do Control Z. I can do Control Z, and now I know the PID of it, right? 30142. So I can do kill -9 3142. And now if I do that again. Now I do a second time, it tells me no such process because I killed it already. So now if I do PSAUX or PS, I don't have anything running. I don't have that running. I killed it. I do jobs. Oh, job with an S. No jobs. So I killed it. Okay, so we did two things now. But I showed you, I think that to me, that's always the most interesting thing, that I can just catch the signal, Control C, it's no longer going to kill it. And I did that here. Let's get rid of this part. Okay, and now what are we doing over here? Here we're doing a complicated program. So let's look at this program. Still going to print hello. Now I say like this. So first I catch Sig and I go that Sig user that prints something. Fine. Then I make a fork and a child. Now, if 0 equals the child, that means I'm the child. Then again, do a fork and print child is running. And again, an infinite loop with a pause. So I'm just waiting here. What about the father? We are the dad. So first he goes to sleep. Then he does some counter. And he does again a sleep. And he sends a kill. He sends Sig user 1 to the child. Now Sig user 1 would normally kill the child, but here it's not going to kill the child. And then I don't know what the rest of this is here.
Are we expected to memorize kind of all of where all the signals do?
No, but you're supposed to know that most signals kill. Most signals, I mean, no, you don't. This first of all, there's only about 2 things they do by default. 2 or 3 things. I'm commenting all of that. So kill. Now I send Sig user to that, to the child whose ID I have. And I do that how many times? 3 times. And the child's going to receive it every time. And he's an infinite loop, so he's not going to die. So let's try running this.
I missed the first part. What's happening for this specific program?
You're about to see what's happening. Now it waits 3 seconds. Now it's going to the loop. No, supposed to print something. Doesn't seem to be doing anything. Okay, so something's wrong. Let's look at that again. It printed that went fine. Then it came to here and it did this thing for, it caught the signal sig user 1. And then it says, make a child. And then it says, if I'm a child, go into a waiting mode. It should print child's running. How come it didn't print child's running? Maybe it didn't. Maybe I need a F flush. I don't see a problem here. Anyone sees a problem? Not even going into the child. Oh, because of this pause. Mhm. Child is running. Oh, there we go. 3 times. Child receives sig user 1. Child receives sig user 1. Child receives sig user 1. That's the father sending it. And he prints child is running. You see that the father is sending to the child sig user 1. And the child is printing child received sig user 1. Again, let's look at it. Here is the father sending sig user 1. Now, and the child gets it and he prints, well, he prints what does he print? He prints whatever sig user 1 tells him to print, which is child received, blah, blah, blah. Now, can somebody tell me what's going to happen if I comment out these 2 lines? What's going to happen now? I took away that signal command. The father is still sending the signal to kill, but the child no longer has the signal command to tell it to what to do when that signal comes. So what's going to happen? Somebody. Nobody knows. Okay. You don't know. I'll show you. Oh, error. Huh? Oh, I know what the problem is. We can comment out enough. Oh no. Should be all right. I mean, I can get rid of that. Well, that shouldn't be a problem. Hmm. This is weird. Cannot open output file. Very strange. Okay. There, look what happened. And see that? Child is running, and then after some time, it died. Why did it die? Because I sent a signal to it. Something is really weird. Very weird.
Uh-oh.
That is very weird. Why can't I get rid of that A dot out? It's like it's owned by somebody. I don't know. That's really weird. Anyway, if we look at the program, if we look at the program, I can't I no longer did this section here where I said the signal for when user one comes is to do this other function. So when the father comes over here and sends to the child sig user one, so the child dies. And then the father eventually dies because he, after a few seconds, finishes his loop. Now, okay, that's the basics of signal. I did not show you an example of sig, what was it? Sig action. But I don't know if I need to really. Yeah, I don't have an example. I could copy and paste one, but all right, that's enough. I think that's enough. No, I'm not going to do that. All right. Sorry, let's. Let's go on to another part of Unix. Just a second. Okay. Now I'm doing a section called System Management. Obviously, I'm not going to do everything there is in system management, but I'll show you a little bit. Well, I want to talk about how Unix works. There's different ways that it works, actually. There's different versions of Unix or of Linux. But you're probably familiar with the term booting a system. Booting a system means, starting the operating system. So technically, it is not the job of the operating system to boot the operating system. In fact, it's a logical impossibility. The operating system can't run the operating system. Somebody else has to start running the operating system. So a special program is needed to boot up a computer. One common bootloader is called grub. Its primary job is to load the kernel into memory and then run the kernel. In other words, you got to copy the kernel from the disk into memory and then run it. The kernel is the main process of the operating system. Once the kernel is fully operational, the kernel looks for an init process to run, which separately sets up user space and the processes needed for a user environment. In other words, it creates a bunch of processes that are needed for a user to work. The kernel itself is then allowed to go idle subject to calls from other processes. Okay, init. So what is init? So the kernel is going to run an init process. The init is a daemon process. And what is a daemon process? A daemon process is a process that is started and then detached to run in the background. In other words, it's not running on any terminal. It's running in the background. We did examples of that with BG, with tilde, with ampersand. Okay, so init is a daemon. This is a process that's running in the background all the time. Short for initialization is the program on Unix and Unix-like systems that spawns all other processes. It runs as a daemon and typically has PID of 1. Okay, right. We said that. 0 is probably nobody, but 1 is the init. Init continues running until the system is shut down. So it's running all the time. That's why some people define an operating system as the one process that is always running on the system. That's a funny definition because it doesn't really explain what it is, but it just happens as a characteristic of it that's true of only it. It's like saying man is a talking biped or a talking animal. But that's not like the full definition of a man, but it's true that that would separate him from everything else. So init is the process that runs all the time. So here it says it's running all the time. Init is the direct or indirect ancestor of all processes and automatically adopts all orphan processes. So if a parent process dies, but its child is still running, and then the child says, "Who is my father?" by saying get PPID, he will get 1 as his PPID because that's init. Init becomes his parent. And as I said, init is started by the kernel during the boot process. Now, some processes are created by init, in which case their parent is naturally init. Init will execute a set of system daemons that are necessary for the proper running of the system. There are different modes the system can run in. These are called run levels. So you can run a system with different set of daemons running. And each set is called a run level. Now, what daemons do I want to be running? So let's think, well, yeah, I'm going to get into it. Yeah. Run levels. A run level is one of the modes that a Unix-based operating system will run in. Each run level has a certain number of services. Services, you can think of daemons, programs running in the background. Stopped or started. In other words, it could be that certain processes I stopped because I'm in run level, certain run level, and certain ones I start. Giving the user control over the behavior of the machine. Conventionally, 7 run levels exist, from 0 to 6. And after the Linux kernel is booted, the init program reads the file called aetc inittab, init table, or init tab for short, to determine the behavior of each run level. Configuration files will tell the system what run level to go to in what circumstances. So for example, here are the 7 basic run levels of a Unix system, and they are 0 for meaning halt. In other words, turn the computer off. It's still on, but it's just everything, all functions will be turned off. There's all processes will cease except for the kernel. Single user mode, maybe even the kernel actually. Single user mode is like what you would know as safe mode in Windows. It means the system is up and running, but you can't have multiple users. Then 2 is we allow local multiple users, but no NFS, no network file system, no network. We have no network. So sometimes if the network is a problem, is not working, you may want to go to run level 2 from run level 3. Run level 3 is full multi-user with network. So actually, typically what happens is when the Unix starts up, it starts at single user mode. Then it moves over to local user and checks that everything works. And then it moves over to multi-user with network. Full multi-user with network. In other words, it may not jump directly to 3. It may first do each of these, and then as it moves from one to the other, it will add more processes and perhaps remove some processes. 4 is not used. 5 is multi-user with a network and a graphical mode and the XDM download manager. No, graphical mode XDM. In other words, it allows you for something used to be called X Windows. In other words, it allows you to export your screen to another computer. So you're not just in a black and white box to type things, but you actually have a full graphical interface. And 6 is an interesting level. It's called Reboot. It restarts the system. So if you say, please go to run level 6, your system will reboot. That's how you, in fact, do a reboot. So tell init is that program that allows you to choose and change what run level you're in. The run level argument should be one of the multi-user run levels. For example, it could be 2 to 5. Usually you would move to one of those levels. You could move to 0, that would halt the system, or 6 to reboot, or 1 to bring the system down to single user mode. So for example, I would type telnet 1, and it would bring the computer down to single user mode. It would disconnect all the network connections. Normally, you would use the shutdown tools, like a program called shutdown, to halt or reboot the system, or to bring it down to a single user mode. But you could write telnet, tell init. Run level is a command to tell you what run level you are in. If you just type run level, you'll get what run level you're in. let's see if I can demonstrate that. Yeah. So here, stop share. If I do run level, tells me 5. And I don't know what the N exactly stands for, but the 5 means run level 5. If I do tell init 1, it says permission denied, thankfully. I would assume that I can't do that. Right? And if I would do sudo tell init 1, it asks the password for Danzig. Well, I can do that. But Danzig is not in the sudoers file. This incident will be reported. In other words, I'm not allowed to do that. So I can't use that. But on your systems, but if I go, wait, what if I go over here? Control here. Now I'm on my own machine. And if I do tell init, well, first of all, let's do run level. Unknown, that's interesting. Tell init 1. All right, it doesn't work on this simple Linux that I have. Okay, so we have this run levels. We have this tell init to change run levels. Run level tells me what level I'm in. And we have init tab. It is used to set the default run level of the system. It's a file. It's usually an etc. And you can define there what, when I boot up, what run level should it go to? And what should the meaning of that run level be? So this is the run level that a system will start up on upon reboot. The applications that are started by init are located in the etc.rc.d folder. So in rc.d, you'll list all of the daemons that I want to be run on a certain run level. Within this directory, there's a separate folder for each run level. Example, there might be in that directory, there might be a directory called rc0.d, rc1.d, rc followed by the number of the run level up till 6. And we have a funny thing. What we do is we append to the beginning of the name of the file a letter K. And files starting with the letter K are to be killed in this run level. Because remember I said, in a given run level, you may stop certain processes and start certain ones. So the ones you want to stop, you put a K in front of. And the ones you want to start, you put an S in front of. And then you put a serial number to determine the order. Use numbers to order which processes come before the other. So if you have one process called 2 and one called 3 and one called 4, so first it'll be in that order, 2, 3, and then 4. Somebody with a very high number will be run later. So files starting with a K are to be killed, and files starting with an S are to be started or run in that run level. Maybe I can show you that. It's not always in the same place, so it may be hard to show you. Not letting me in. All right, forget that. Trying to get in, couldn't get in. Okay. So we're back to this init tab. Any file starting with a K is to be killed. Any starting with an S is to be started. Use numbers. The lower numbers come first. Some systems including linap, uses a set of files in etc init, not in etc rcd, instead of using init tab. So here's, for example, here, the format is ID, run level, action, and then the process. So for example, this is like L0, that means run level 0. Level 0 is process is 0, is level 0. And the action to do is wait. And then this is actually lists the files that you should run in it in RC0. Right? The ID is a unique sequence of 1 to 4 characters, identifies the init. Run level is the run level which the specified action should take place. This file may contain multiple characters for different run levels. For example, 1, 2, 3 specifies the process should be started in run levels 1, 2, and 3. So here, so first we can talk about what does this wait mean? So this wait means the process will be started once when the specified level is entered, and init will wait for its termination. So it will keep running. Once, the process will be executed once when the specified run level is entered. Boot, the process will be executed during the system boot, and the run level field is ignored. So now only do it when you boot. Init default specifies the run level which should be entered after system boot. All right, again, to get too technical. But it gets very technical here. This init tab explained. On the left side of the file listing above are added numbers to help describe the line. So I added those numbers. On line 1, you can see ID 3 init default. So let's go back there. ID 3 init default. What does that mean? The ID is ID, which stands for init default. ID doesn't mean identification here, it means init default. So in other words, like the ID here is L0, here the ID is init default. And guess what 3 means? 3 means the default is run level 3. Let's see if that's what I write. The ID is ID, which stands for init default. Note that it is unique on all the other numbers. It is unique on all the numbered lines. There is that field is unique. The run level is 3, which sets the default starting run level to run level 3. In other words, when I start the computer, I'm telling it, go to run level 3. The action is init default, which tells init to make the run level the default run level. Right. I don't know, right. The action, I don't know why. See, the name is irrelevant. The name is just the name I gave it. I called it init default. But really, here's the action, init default. So whatever entry in this file that has the init default is going to be telling the system what run level to go to when I start up. Note that the process field is blank since it is ignored by the init default action. Right? There's no listing of what processes to run because that's actually going to be whatever 3 is. It's going to run these processes that are in this place, in RC0. Line 2 tells it to run the program etc rcd rc system init during system boot before any other process. So let's look at line 2. It says always run this process, system init, system initialization. That's because of this keyword system init, not because of the SI, because of the system init. Telling you where, basically saying what is the initialization program. Lines 3 to 9 tell init to run the program etc rcd/rc for run levels 0 through 6. Note that for each line, the appropriate run level is passed to the RC command. In other words, what's going on here? What is this 0 here? Why is it not? What it's saying is run the command in run level 3 rc.drc with the parameter 0, which tells it to run which tells it to run all the things in a certain directory, all the programs in a certain directory. And this says if it's level 1, tell it to run. Now, theoretically, I could mix up everything. I could say in run level 2, run everything that's RC 5. I don't have to tell it in 2 to do 2. I can tell it 2 to do 5, and 5 to do 2, and then 4 to do 3. Yeah. As we're giving me a certain amount of flexibility. Okay. Okay. So like we said, lines 3 through 9 tell it what to do, tell it to run this program, RC, with the various parameters. For example, on line 5 above the second field, the run level specified 2. At the end of the line, there is a space and a 2, which allows the variable 2 to be passed on the command line to the program and tells the program knows to mean run things at run level 2. I wish I had. Yeah. So here, this is what I want to show you. If you look at the contents of etc rc3.d in directory in the Linux system, you will see a large collection of both kill and start scripts that determine what is shut down and what is running. And here I don't know why I wrote 2 here and then I wrote 3 here, but it doesn't matter. Here is the contents of rc2.d. You see it has a K followed by a 0, there's 0, 1, and then DNS mask. I don't know what Avachid, Avachid, I don't know what that stands for. These are different programs. But the important thing is this says K means kill. Kill, and it tells you the order. Now remember, run level 2 doesn't have DNS, doesn't have internet. So I'm going to kill the DNS, whatever this program is, some DNS program. So I'm going to kill that. That's what K means. And 01 means first kill it, then kill this. Now, if there's 2 with the same number, it means I don't care what the order is. Could be this one first or then that one first. But first kill this one and then kill all 3 of these. And then 36 is obviously bigger, so it'll kill this one. Then it'll kill this one, then this one, then this one, then this one, and then this one. So it'll kill all of these, ending with the 91, whatever capi is. I don't know what these are disk. All these programs will be turned off. And what will be started up? 15 is the first one will be started up. And the last one is 26. And what is it? MD monitor, Bluetooth. So you see, this is very flexible because I can say any programs I put here with an S will be started up. You know, I can add things to my system so that automatically some program will be started whenever I go into run level 2. I can also make, you know, run level 2 be just like run level 3 if I want. Anyway, that's the idea of these K and S files. And that's what I'm doing when I say over here, run RC with parameter 2. That means RC, when it gets the parameter 2, it knows to go to the directory etc rc2.d. And then it finds all of these things and runs all of them and kills the right ones to kill and runs the ones the right ones to run. So you see, we're defining how the system comes up. It has first it starts this, and then based on what this number is over here, this 3, it goes to that run level. Now, I believe, somebody can correct me if they know better. I believe that if you say, I believe that if you say go to run level 3, it'll first run all the things in all the preceding run levels. I'm not sure about that. Now, line 10 specifies that the program sbin update will run once for every run level. Let's look at that. Notice there's no number here. In other words, this sysinit will also run for every run level. But also here, this will run once for every run level. There's no level here. It'll run sbin update. I guess it'll look for updates. Line 11 sets up the program sbin shutdown to run when someone on the system console, on the main keyboard, the system console, presses Control-Alt-Delete combination. So that's how it gives you that Windows type behavior. In other words, you have this is only on Linux, but it's not a Unix thing. You have this special word here, anytime the special word Control-Alt-Delete, it's special keyword. That means if for any run level, if somebody types Control-Alt-Delete, then run this command. Shutdown, time, I don't know what T3 means exactly. I'm not sure, but now I know what that means. That means do it now. So shut down now, essentially. I forget what T3 and -R means. This is a program called shutdown, which shuts the program, shuts the computer off. Essentially goes to the run level What is it? Run level 6? Yeah, or actually 0. Oh, I don't know. Yeah. See, 6 is to reboot, so it's 0. Okay. So that's the special control alt delete command. Essentially, I could write something else here. I could write that when it hits control alt delete, run a program that I wrote that prints hello world. And then control delete would cease to work on that Linux machine. It wouldn't shut down the computer. It would just print hello world. All I'm doing is I'm saying when control alt delete happens, run this program with these parameters. See how simple it is. Right. So according to this program, what's going to happen is first we're going to run sysinit, because that was said to be run the first. Then we're going to run update, and then we're going to go to run level 3. We're going to run RC with the parameter 3, because we said that that was the default. Therefore, the next thing the system does is to run sysinit, the sysinit file, save buffers to the hard drive, then run system script files for the requested run level, which will start up many system and network services. Right. So maybe I won't run 1 and 2 beforehand. Okay. So what is this RC command that we saw? Basically, we saw that we're running this RC command. It's not Royal Crown Cola or Royal Canadian Cola. RC run with the 3 as its argument will run all the scripts in the rc3.d directory. That's the whole point of it. It will run the kill scripts, those that start with uppercase K first, and then the start the scripts, then the start scripts that start with those that start with an S. And it'll do something like this. As the program will essentially be a for loop for everything in RC $run level, whatever that run level that I got at 3.d K starts with K, and then do, and then I'll type $I to run it. I don't know why I stopped here. It should be like it should be here $I. Actually run it. And here we saw this already. Okay, now I have to let you down, which is, that's an important concept to understand, but inittab has been replaced on most Linux distributions. It's not really used so much anymore. The positive thing about this system that that I just described is that the scripts are editable text files, assuming you have root privileges. So you can see exactly what scripts was trying to do. In other words, you have total access. You can see all the scripts. You know what are all the files in that directory, and you can edit them and you can change things. The negative thing is that over time, the scripts become complex and hard to understand. In other words, the order might be, I don't know exactly why the script will become hard to understand. The system doesn't have a direct method of representing dependencies, such as don't try to update the system clock from the network until the network is actually up and running. How do you can't tell it that directly. What you can do in the system we described is just make sure, you'd have to see, that's the thing, you'd have to write this is what I mean by saying the script's complicated. You'd have to write a script that first ran the network connections, and then set a variable as success, and then have at some later point, if success, then try to update the system clock from the network. So it's going to get complicated if you have to build all your dependencies yourself. So systemd is a package of programs used for just about all process control, not just startup. So systemd is another way of running a system that has like it's all binary files. Instead of being text files you can edit, it's like pre-built stuff. And it's actually, I think, more complicated in a certain way. So systemd is a package of program used for just about all process control. Processes have a service declaration file, which defines the conditions under which the process is started and stopped. Okay, so you have some kind of declaration file. When do I start and when do I stop? For example, here you can define dependencies. You can say, only start this process after this process worked. So you do have that ability to define behavior in a not in a code way, but in a linguistic way. A service declaration file is not a bash script. It is interpreted by the systemd binaries. In other words, instead of writing a bash script like I just showed you, I could write with the loop. I'll actually just write certain information, and then a binary file will read that file. A program essentially will read that file and to do what it's supposed to do. Logging in systemd is not by text to a system log file, but in a binary form to a systemd log, which you can't access. So you can't just look at it. You can't just cat it. It'll be meaningless because it's a binary file. You can only look at it through a systemd utility called journal control. Journal control. Systemd provides a declarative way of defining startup and other process dependencies. As you can say, I want this to be in front of that. That is good. But the actual execution of the systemd binaries and the logs produced are more opaque than under the previous system, which tends to make system admins a bit nervous. In other words, the system that I just described, I can see exactly what's happening. I can check which files are running on any run level. Here, I just have these declarations, and the system knows how to read those declarations and run it, but I don't necessarily see all the processes that are running. It is a standard part of most Linux distributions now. This is a paraphrase from John Connor at Quorum. But that's why I didn't understand why one thing I wrote there. So here we're getting into how we actually define these dependencies. But actually I want to stop here because we should have a lab. So we'll talk more about systemd next time. Avraham, you probably know all about systemd.
A little bit, not much.
Not much? Your system is running systemd?
Yeah.